Hello everyone! The effect I'll be creating in this video falls into the category of image distortion, that is, a simulation of an imperfect display or external interference. As we can see, this interference resembles frequency modulation of a signal and is based on a similar principle. So let's take a look at how this algorithm works. And once again, I'll create a new scene with the usual image in the background, that is a screenshot from our game Whispers of Prague. So we'll do all the preparatory work, meaning I'm right-clicking on the scenes folder, create new scene, it's 2D scene, let's call it frequency distortion. Okay. And I'll drag the mentioned image into it, so the sprite 2D node was automatically created. And in the inspector, let's do the usual stuff, canceling centered for the offset, and in the transform position or reset position to 0, 0. Okay, and scrolling down to the material section where I create a new shader material, click it and create a new shader, which is of the type shader, mode canvas item, name frequency distortion.gd shader, and I'll just change the folder to shaders. Okay, create and click again to open it in the shader editor. And as always, I'll delete everything from the generated code that we won't need for our effect, leaving only the fragment function. So I'm deleting vertex and deleting light. Excellent, we can start coding. The beginning of the fragment function will be the same as in other tutorials, namely the definition of the UV coordinates and the image resolution. And as usual, we'll obtain both from the internal variables UV and texture pixel size, which are available in this function fragment. So it would be vec2 UV is UV in uppercase, and vec2 resolution equals 1 divided by texture pixel size. As you probably noticed at the beginning of the video, the effect is not static, but changes over time, so we'll need a parameter to control the speed. I'll therefore add it as a uniform parameter. So I'll add it here at the top, a uniform float speed with a hint range, and the initial speed I'll set to 0, and let's set the range from -50 to 50 with a step point 0, 1, of course. Okay, notice that I set the hint range from -50 to 50 so that we get movement in the opposite direction for negative speed values, or we can stop the motion entirely when the parameter is set to 0, which is the default value. And now I'll use this parameter in the code so we get a variable that changes over time. Float time is time, internal variable, times speed. Okay, let's move on. The effect is based on modulation by summing the values of pixels to the left of the current pixel. So we'll need a variable that acts like an accumulator. I'll call it result. Float result is 0. And once we are done with the calculations, we'll display the result as a grayscale, like this. So internal color, which is the output, is, as we know, vector 4, that consists of vector 3 result and 1 for the alpha channel. So we are creating a vector 3 with all three components the same, which is equivalent to a shade of gray. Okay, so let's move on to the actual computation. And of course, now everything is black because we are using the initial result value, which is 0. So, since we are working with grayscale values, we'll need a function that returns the shade for a color pixel. You may remember that in some tutorials I worked with so-called luminance, which produces grayscale values that are more pronounced to the human eye. This time, however, it won't be necessary, because after summing many values, the difference would be practically negligible, so we can get by with a simple arithmetic mean of all three color components. I'll write this as a new function and call it getShade. And let's put this function just above the fragment function, so it would be float getShade, where shade, where the input parameter is vector for the pixel color, and as I said, the arithmetic mean. So we return pixel R plus pixel B plus pixel G, the RGB colors, divided by 3. Very well, let's return to the fragment function, where I'll write the basic algorithm, namely summing these shades for all pixels to the left of the current one. So it will be a loop like this. For float x starts from 0 and x is less than equal to frag chord.x, x plus plus, and some cycle. Very well. Notice that I use the internal variable frag chord, which takes values according to the actual dimensions of the image. So along the x-axis, it's from 0 to 1919. In this case, that's more convenient than normalized UV coordinates, because we'll be working with the values of individual pixels, so iterating with a step of 1 makes more sense. Okay, and now we'll perform the mentioned calculation. First, I determine the coordinates, then I read the pixel at those coordinates, and finally, I add the result of the getShade function for that pixel to the accumulator, like this. Vec2, let's call it chords, is vec2 and x divided by resolution x, UVY. Okay, we are using this division because we are supposed to use these coordinates in the texture function, and texture function works with normalized UV coordinates, so that's why. And now let's do it. Vec4 pixel is, as I said, is it pixel? No, sorry, pixel texture function applied on our texture and chords, our new vector. Okay, and finally, let's add it to the accumulator. So result, I said, is increased by the function getShade applied on the pixel, sorry. Okay, something changed. Yeah, as we can see, the result is white for all pixels. That's because the value in the accumulator, the result, has significantly exceeded 1, which corresponds to exactly this outcome. Color 111 is, of course, white, and everything above that is white as well. So, to get something displayable and at the same time introduce the frequency modulation I mentioned at the beginning of the video, let's try applying the sine function to the resulting value of a result. So right after this fourth cycle, where the accumulator is finally accumulated, let's do what I just said. The result is sine of a result. Okay. Very well. That's definitely more interesting. Let's show more of that. Okay. This is fine. This is definitely more interesting than the previous white image. If we tried hard enough, we might even be able to recognize some shapes in this chaos. However, yeah, something like here resembles the fountain, I guess. However, we are not done yet, and we'll need to make a few more adjustments. Let's add our time value to the sine function. So it would be result plus time. Okay, nothing happens because the speed parameter is set to 0. Let's expand shader parameters and let's change it and the effect should start moving. Yeah, can you see it? Moves nice. And the negative values mean the moving in the opposite direction. So let's reset to 0. And it would be good to modulate the frequency modulation using an adjustable frequency. So let's add it as the second uniform parameter right here. Uniform float frequency with a hint range and the initial frequency I think I set to 10. And this time the range would go from 0.1 to 20 with the step again 0.01. Okay, and I'll use it in the code. So scrolling down to the fragment function, and here result plus time would change to result times frequency plus time. Okay, something definitely changed again. And we can observe that changing the frequency parameter also changes the structure of the effect. Now I'm increasing, now I'm decreasing. Yeah, very well, resetting to 10. However, the distortion is too strong and the original image gets completely lost in it. So we'll need to make another adjustment, namely incorporate the original image into the algorithm, like this. Okay, so after calculating the result, let's add one more line. A result would be multiplied by the function getShade applied on texture function of our texture and UV coordinates of the current pixel. Okay, now we've got almost exactly what we saw at the beginning of the video. The result is quite dark though, so let's introduce one more parameter to control the contrast. Uniform float contrast with a hint range, and the contrast would start at 0.8. All right, and it goes from 0 to 1 with the parameter, with the step 0.01. Very well. And let's add this parameter to the code. So this final calculation would be modified slightly. Let's do this 1 minus contrast plus contrast multiplied by this getShade. Okay, that's definitely better, and I guess we are done. So I think if we change the contrast, we can see how it gets brighter and darker, but I guess that the value 0.8 gets a pretty decent result. All right, let's start the animation. Now the frequency distortion is actually in action. And if we play with these values, we can observe how the individual parts of the image are being modulated. So I'll zoom in, for example, this one with the lantern, and we can see it here. This goes to the left, this goes to the right, and basically the power of the modulation is based on the actual pixel color. So we get these interesting frequency modulated patterns. Okay, and I hope they are also visible on YouTube, where they might have been additional distortion due to video compression. Okay, one more thing. Let's get back to the original zoom factor. If we want to preserve the color image, we can change the last two lines accordingly. I'll do it right here. Okay, so I will simply copy and paste these two lines and comment out their original values. All right, and now instead of a result, we'll define a vector3 color and do it right like this. Vector3 color is a result times everything else, but this time we need to work with the actual pixel in RGB color. So instead of getShade, we will keep this function and use the RGB suffix to reduce it to the red, green, and blue components. And instead of result, we can replace this with the color. Wait for it. Yeah, now we can see it, how it's pretty colorful. And if I zoom in, we can also see the distortions just like before, but everything is in color. But of course, if you prefer a black and white image, stick with grayscale. So let's just get back, resetting everything, reverting, and now we have the original effect. Great. Thank you very much for watching. I believe this kind of effect can be useful if, for example, we have monitors in our game that display footage from other parts of the scene and we want to simulate signal interference due to, let's say, radioactivity or some kind of enemy sabotage. If you're working on a game where this shader could be used, I'd be delighted to read about it in the comments or on our Discord server. And once again, I'll add this shader to the Godot shader pack product, which I link to in the video description. Anyway, take care, good luck with your projects, and I'll see you in the next video.